Hi everyone. So today I'm going to talk about the calculations involved for motion graphs. So we'll start off with this very familiar velocity time graph. Say we are looking at an initial velocity here, I'll label it as u, and a final velocity here, I'll label it as v. And this takes place across a certain time interval. So let's see what happens if we take the gradient of this velocity time graph. The gradient here, the equation will be the final velocity minus the initial velocity divided by time interval. And hey, this equation actually looks pretty familiar. This is simply just your acceleration value. So we have then established that the gradient of a velocity time graph will give us the acceleration of the object across the same time interval. So let's proceed on to our second learning objective. Let's look at this acceleration time graph for a constant acceleration object. So say if we want to find the area underneath this acceleration time graph for this particular time interval, the acceleration value is a. The area under the graph will therefore be acceleration multiplied by the time interval, the area of this rectangle over here. As you can see, acceleration times time interval can be seen in this equation. So a times triangle t simply gives us velocity minus u, and actually this right hand side of the equation is simply the change in velocity. Therefore, we have now established that the area underneath an acceleration time graph will get you the change in velocity. Now, we can extend this area underneath the graph concept to the velocity time graph too. So say we are looking at this area of this triangle over here across this longer time interval, triangle t prime. Now, this area of this triangle will therefore be the change in position of the object across triangle t prime. And this guy over here is simply just the displacement of the object from time 0 to this point in time. Now, we can also apply the gradient relationship on the position time graph. So look at this new position time graph that we have over here. Say I am interested to find the gradient at this point over here. I will first draw a tangent, and then by drawing a gradient triangle, I can then figure out what is the gradient of this tangent to this point on the graph. And this gradient over here will actually be equivalent to the instantaneous velocity of the object at this point in time. So to sum up what I have just said, basically we have position data, we have velocity data, and we have acceleration data. So say we are only given the position time graph. To figure out the instantaneous velocity, we need to find the gradient at the particular point in time. Given velocity time graph, if we do the same thing, we find the gradient at a particular point, we are actually figuring out what is the acceleration value. Now, from the acceleration time graph, if we want to find the change in velocity, then we have to find the area underneath the graph. Be very careful that this area doesn't tell you the actual velocities, but rather it tells you just the change in velocity. Similarly, from the velocity time graph, if we find the area underneath the graph, we do not get the positions, but rather we are getting the change in position by looking at the area underneath the graph. And this change in position is just the displacement of the object across the same time interval. That's all I have for you today. I will see you the next time.